Urban heat domes are a global challenge that many cities around the world face. Urban heat domes are urban areas that are warmer in temperature than its surrounding rural areas due to human activities. They can also be known as urban heat islands. The yearly average temperature of a city with 1 million people can be 1.8 to 5.4 degrees warmer than its surrounding areas. This contrast can be greater at night or during the winter, when it can reach as high as 22 degrees contrast. There are many causes of urban heat domes. One of these is a lack of vegetation. Lack of vegetation leads to less shade in a city, which can decrease the amount of cool spaces, as well as the lack of evapotranspiration, which releases water into the atmosphere. The second is the modification of land surfaces. With the introduction of streets and skyscrapers, there's many more surfaces to hold heat, and these surfaces hold more heat than previously before. The third is buildings blocking air circulation. Tall buildings can block air circulation from passing hot air out of the city and cold air into the city. The fourth is dark surfaces holding more heat. Dark surfaces, like concrete, can hold 2,000 times more heat than that of air. Some organizations that are currently doing something to help are the Environmental Protection Agency, Tree Utah, Lawrence Hall, and the Heat Island Group. Some solutions that these organizations have proposed are white roofs, which reflect rather than absorb heat energy, green roofs, which are covered in vegetation that absorb and use heat energy, planting vegetation around the city, which increases shade as well as increases evapotranspiration, and green parking lots, which hold less heat energy and reflect more heat energy. Urban heat domes have impacts on both humans and the surrounding environment. They impact both water and land habitats of animals, as well as humans in cities and surrounding areas. Species that are good at colonizing can utilize conditions provided by urban heat islands to thrive in regions outside of their normal temperature range. One of these species is gray-headed flying foxes, a bat species native to Melbourne, Australia, which can now colonize urban habitats due to the increase in temperatures there. Another part of the environment that's affected by urban heat domes is water temperature. With the temperature of nearby buildings sometimes reaching over 50 degrees different from near surface air temperature, precipitation can warm rapidly and run off into nearby streams. This precipitation can increase the water temperature by 20 to 30 degrees. This causes fish species in the body of water to undergo thermal stress and shock, which can often kill fish. Another part of the environment that urban heat domes affect is heat waves. As urban heat domes are characterized by increased temperature, they can potentially increase the intensity and length of heat waves within cities. The nighttime effect of urban heat domes can be even more harmful during a heat wave, as it deprives city residents of the cool relief found in rural areas during the night. Increased temperatures have been reported to cause heat stroke, heat exhaustion, and heat cramps. Severe heat stroke can also lead to permanent damage to organ systems and early mortality. 1,000+ people die each year due to extreme heat. High urban heat island intensity correlates with increased concentrations of air pollutants that gathered at night, which can affect the next day's air quality. These pollutants include volatile organic compounds, carbon monoxide, nitrogen oxide, and particulate matter. The production of these pollutants, combined with the higher temperatures in urban heat islands, can quicken the production of ozone. Ozone at surface level is considered to be a harmful pollutant. Our proposed solution works similar to that of a refrigerator, except that it redistributes heat from higher, colder areas into the lower, warmer areas of cities. It appears as a tower with the simple parts of a refrigerator, like a compressor, condenser, evaporator, expansion valve, and the coils. High in the atmosphere, where the air is cold, it would begin the normal process you would see in a refrigerator. The low-pressure cooling vapor would be condensed into a high-pressure superheated vapor. This would then travel down the evaporator, working its way into the city as it turned back into a cooler liquid. This would then go through the expansion valve, turning back into a super cold, low-pressure vapor. This would cool the surrounding air and then travel back up to the top of the tower to redo the cycle. It would be powered by solar panels on rooftops adjacent to it, which would also reflect or absorb heat, reducing the overall temperature in the area. This graph shows the urban heat island effect on cities across the Japanese island of Kanto. This period spans from 100 years, starting in 1907 and going all the way to 2007. The cities shown are Yokohama, Tokyo, Kumagaya, Maebashi, and Katsura. All these cities increase in temperature by roughly 3 degrees over the 100-year period, and in some cases all the way up to 3.5 degrees. This is an example of an urban heat island profile graph. This is a practical way to visualize the urban heat island effect in your own city. You measure the temperature in certain parts of town and you fill it in on the graph. Thank you for watching our educational video on the effects of urban heat islands and the causes of urban heat islands.